All right, so for today's warm up, we're going to talk about problem three and problem set three. I chose this one because it's a little bit more challenging, and there's an interesting question here for question C here. But right now, what we have here is a boy riding a shopping cart. So they're both traveling with the same speed since the boy's standing on the cart, and then the boy kicks off the cart and he lands at the ground with a velocity of 0. And we want to know for question B just what's the velocity of the cart after the boy jumped. Okay, so setting up our momentum chart to start, first we have to take note of the boy's mass, which is 70 here. So I'm just going to go here and just go 5 for 70 kilograms. And we know that the boy is riding the cart. So I'm going to call this up here just 2 meters per second. All right. And if you want, you can just call this 140 kilograms times meters per second of momentum. And let's draw the one for the cart. So the cart's not going to be as wide, but it's going to be just as tall up top because, again, they both have the same velocity of 2 meters per second, but the cart has a mass of 50 kilograms. So the momentum of the cart is just 2 times 50, which gives us 100 here. Okay, now this is the problem. All of the problems on problem set 3 have no impulse. Okay, so you can look at all the problems, and then again, you'll see that none of them mention force, none of them mention time. So we can't, they're not impulse problems. All the problems on this problem set give you two masses, and then they give you some velocities. Okay, so let's diagram the final part, the momentum here. Now here, we've got still the same mass for the boy. Well, this one's going to be 70 kilograms. So nothing about the boy's changed except for the fact that he's now not moving. So that's why the velocity is 0. So for the carts, we have a momentum, and it's got a mass of 50 kilograms. So we want to know just how tall this is. And let's talk about this real quick. I know it's going to be faster than before. Okay, and here's why. If you take a look at this momentum chart here, the total momentum in the system is going to be 240. Since there's no impulse, there's an impulse of 0, we have to have 240 total at the end somehow. Now, the cart cannot have any, the boy cannot have any because he's at rest. So all of this 240 has to go to the cart. Okay, so that's the key part there. All of that 240 has to go to the cart. And then we can set up our equation here. So the momentum of the cart is equal to 240, but that's also equal to mass times velocity. So we already know the mass is 50 kilograms, so we just need to figure out the velocity. So if we divide the 50 over, we get a velocity of 4.8 meters per second. So it did indeed go faster. Okay. Now, this is one thing I wanted to talk about for question 3, and it's basically about this whole momentum conservation thing. So we want to figure out like the impulse that the boy did to the cart. Okay, yes, there is no impulse on the system. Okay, if we define the system as both things. Okay, but if the system is just the cart, so I'm going to ask you to focus on just the blue here. So the blue had 100, and now it has 240. Okay, so right there is the change in momentum of the cart. was that it increased by 140. Okay, so that's the answer to C, is that the cart by itself did experience an impulse, right? So that blue box did grow and it gained 140. So how did it go about doing this? Well, it happened because if we think of the boy and think about the boy's change in momentum, we see here that the boys started with 140 and now they have zero momentum. So their momentum dropped by 140 kilograms times meters per second. Okay, so that's something that we have going on here, that the loss in momentum for the boy was a gain in momentum for the cart. Okay, so that's just one thing I wanted to show you. That's why I chose problem 3. So hopefully this helps out with 1, 2, 4, and 5.